We have Patrik Krcelic, who's a final year PhD student at the University of Southampton, studying the dynamic fine-scale electric field in the ionosphere. Patrik's work includes the expert analysis of auroral observations from the ASK instrument located on Svalbard to explore this fine structure and variabilities. So over to you, Patrik.
Hi, thank you for this introduction. Like Jasmine said, I'm Patrik, final year PhD student. I would like to thank the MIST Council for inviting me to give you this talk about fine-scale auroral dynamics. So, as most of you are aware, in the polar cap, there are two main things driving the dynamics. One of them is polar cap potential, showed here on the right for various IMF conditions. And we have the ion drifts along these equipotential lines. The second thing that's affecting the ionospheric dynamics in the polar cap is various current system. Now, both of those are causing the ion drifts and changes in the ionospheric conductivities. Now, because we have a big ionosphere which is quasi-neutral, the ion drifts are only affecting ions. And we have the neutrals which are affected by the neutral winds. And because of that, we have the discrepancy between the neutrals and the ions. We have collisions and we have transfer of energy. And we have the increase in the temperature of the neutrals, which we call the Joule heating. Here is the image of a Weimar model. So on the left is the polar cap potential, and on the right-hand side of this panel is the associated Joule heating in the polar cap. Now, the main problem here is that we have major uncertainty in estimates of Joule heating, especially for the substorms. It seems that we are missing some energy. So when you calculate the total energy coming in and what is deposited into the polar cap, we are missing something. And one of the ideas is that it might be that we are underestimating the Joule heating, and the possible solution is inclusion of the local and time varying electric fields. So aside from cross-polar cap potential, we also have the auroral systems, and these are the two. On the left here, we have the two main types of the current system causing the aurora. We are more inclined to believe that the second type is more correct. In the middle here is basically the same thing, it's just a cross section, and you can see that the aurora is associated with this upward current, and then we have the ionospheric perpendicular current or Pedersen current, and the electric fields associated with that current will cause the ion drifts. On the right is the same representation, but in 3D, and also when we have the upward current, we have a pair of downward currents causing these Pedersen currents on both sides of the arc pointing toward the auroral arc. But this is only true for the average case, or if you are looking at a more global picture. And even when we include those into our Joule heating estimates, we still have underestimates. And the main idea here is that we are averaging, and my PhD is basically looking at the things without averaging, and we are doing that by using the ASK instrument, which is Auroral Structure and Kinetics. It is located on Svalbard. It consists of 3 cameras, each of them observing one distinct emission. 2 of them are prompt emission, and 1 of them is metastable emission. So what does that mean? So the prompt emission has effective lifetime of a few nanoseconds, and we treat them as instantaneous, and it is ASK1 and ASK3. And you can see here that the features present in this time step are no longer present in the subsequent time steps. And these 2 prompt emissions are carefully chosen because from their ratios, we are able to calculate the energy and the fluxes for each pixel of our image. Metastable emission, however, has a time of life of 5 seconds. And as you can see here that the feature present in this central time step stays for a while, and we are able to trace it in time. It is also the ion species that we are tracing, so each movement is due to ion drift. So first thing that I'm going to present to you is the statistical study that we did. We observed the small-scale auroral arcs. Our goal was to better understand the electrodynamic drivers behind the arcs and electric field, and maybe try to explain the source of high small-scale variability. So this is one of the example events just to explain what we do. So this is the event from 1st of February 2017. We have our 3 ASK cameras, ASK 1, 2, and 3. And during this event, there was a telescope present on ASK 2. So the black rectangles on ASK 1 and ASK 3 are the field of view of ASK 2. Okay, so first and foremost, like I said, from the prompt emission, we're able to get the fluxes and the energies. This is the picture showing the fluxes, but we're also doing some transformation to get rid of the lens effects of the camera. So what we have here is the top view along the magnetic field lines. And from these fluxes, we're able to get the direction of the arc, and then we define the normal and tangential coordinate system, which is going to be important later. Also from this, we are able to get the mean flux within the arc, and also the standard deviation, which we use as a proxy for variability. But we don't just take it from one frame. We take that from all the frames within our event, as shown in this video. So the mean value is the mean flux of the event, and the standard deviation, we assume it's the both temporal and spatial variability of the event. And then we repeat the same thing for the energies. Okay, when we model the second channel, however, so on the left here we have the observed ASK2 image, on the right is the modeled, and from this model we treat ion drifts as a free parameter and trying to match the model and observed image with a mean square by minimizing mean square error. So on the right-hand side here, we have the velocities associated with our event. So the color bar here indicates the time step, and these velocities are in northeast coordinate system. And from this picture, you can see that there's a lot of variability in the velocity. Now, we use the orientation of the arc to separate our velocities in normal and tangential direction. And the reason we do that is because in some cases, but not in all events, but in some, we have very poor signal-to-noise ratio on ASK2 channel, and it causes some synthetics in tangential direction. And we have decided to ignore them for now and just focus on the normal direction of the ion drifts. And here we can see the mean value is with black vector, and the dots are representing the variability in two directions. So in total, we have 6 variables that we are observing. So the mean flux of the event, the standard deviation of the flux, the mean energy, the standard deviation of the energy, and then the normal direction of the ion drift, mean value, and standard deviation. We have 23 events, and because we have 6 variables, we have 15 tests in total. So we are testing all the pairs, and we're also using some thing called Bonferroni correction. I'm not going to get into too much detail, but when you're doing multiple tests, you need to do this correction to make sure you're not going to get false positives. So our alpha corrected here on the bottom is 0.003, and if we have a correlation which has a significance level below that, we say we have the significant correlation. So as you may assume, most of them are uncorrelated, but there are 2 significant correlations, and we are testing our correlations using Spearman and Kendall tests. So on the left here, we have the mean flux and the variability of the flux, which seems to be correlated, and we explain those by basically acceleration processes, meaning that the higher acceleration we have, is going to cause more variability because not all the electrons are going to get equally accelerated. Some of them are going to get less, some of them are going to get more, depends on the conditions, but the more dynamic event seems to be, the more intense event acceleration seems to be more dynamic. On the right here, we have something very interesting, and that is that we have the variability of our drift seems to be correlated with the variability of the flux. And that one surprised us when we first saw it, but then we tried to explain it, and we think we found a good explanation for it. And if you look at here, we have the upwelling current sheet. On the bottom here is where the auroral arc would form, and then the blue vectors are electric fields. So this is when you have static and uniform current sheet, and you can see that we have static electric field. If we have dynamic and uniform current sheet, you can see the changes of the intensity in the current sheet. You also see the changes of the electric fields, but only in the normal direction. Now, bear in mind that we are looking at variability of the normal component of the ion drifts, which is caused by the variability of the tangential component of the electric field. And here we don't see that. However, if you look at the dynamic non-uniform current sheet, we have the tangential component or tangential variability of the electric field here. This dynamic non-uniform current sheet would also affect the fluxes, and it would cause the high variability of the non-uniform current sheet would cause the high variability in the flux. And that is our main explanation here. So this is just to show you what we are observing with this in this black frame. This represents the field of view of the ASK instrument. So our possible explanation for a correlation is that variability of the non-uniform and dynamic current sheet would be the source of variability in both precipitating electron flux, and it will also be the source of variability in tangential electric fields. And this is why we have the correlation between those two variables, because they have the same source. And here I have included event from earlier, just to show you that this is real time. This is 4-second event, and you can see that current sheet associated with this event is probably neither uniform nor static. But you may ask yourself, why do we care about this? Okay, we have high variability in electric fields. What does it matter? And this is where we did a case study in which we estimated Joule heating profile in the upper atmosphere. And we did that by analyzing two auroral events from early February 2017 to show the effects this variability would have on the Joule heating estimates. So this is the formula for the Joule heating. We have Pearson conductivity, electric fields, and neutral wind. For now, we are ignoring neutral wind because they usually take a couple of minutes to 10 minutes or even half an hour to respond. But we are observing events which are a few seconds, 4 to 5 seconds. So we are basically ignoring the neutral winds for that reason. We are calculating electric fields using ASK, and also we are measuring ion temperature and electron density using ISCAD, and use those to calculate the Pearson conductivity. So the first event we are analyzing is the same event that I used earlier as the example. This is just to remind you how it looks like. It's from the 1st of February 2017. These are the velocities that we get from modeling. And then these are the ISCAT measurements. So on the left is the electron density profile. On the right is the ion temperature profile. There are two profiles because ISCAT measures in 5 seconds time intervals, and our event is just between the two. So the first 2 seconds we need to take the black profile, and the other 2 seconds we need to take the blue profiles. So there's not much difference between the two profiles, but because we have the ASK and ISCAD measurements, which both come with their uncertainties, we are able to basically do the Monte Carlo simulation. So we are running 1,000 Monte Carlo profiles for each time step, and if we average these 1,000 profiles for each time step and then average those profiles for the entire time interval by height, we get what we have here on the left, which is the average Joule heating profile during our event. Now, this doesn't mean much because most of the measurements are looking at the height integrated Joule heating profile. So when you have these 1,000 Monte Carlo profiles, if we height integrate each of those, we're able to get the distribution for each time step. So what we have here is for each time step, we get the normalized distribution with values here in represented with the color bars. The red line is the peak of the distribution. The black is solid line is the median value of the distribution. The dotted lines are the dashed lines are upper and lower 25%, and the dotted lines are upper and lower 10% of our distribution. And one thing you can see here that we have some gaps, and in those times our uncertainties were higher than mean values. So this is why we decided to proclaim them as unreliable and not to take them into our analysis. And the second thing you can see is that we have the values of around 150 to 200 milliwatts per meter squared, which is much higher than what is normally measured by radar data, especially around Svalbard. In the extreme cases, we get the values of around 10 milliwatts per meter squared. So we have very significant heating here because we're observing this very valuable event with camera. Second event, which we decided to look like it's a bit more dynamic, it's from 2nd of February 2017. We decided to double check our findings on the second event. This is how it looks like when we model it. Again, on the left is observed and on the right is the modeled emission. This is how the ASCAT measurement looked like. Now you can see here that you look at the electron density profile, that in the second time interval we have the increase in the electron density, and this is going to be important. So this is the same as we had before. So this is the 5-second event. Again, the distribution, we have normalized distribution for each time step, and you can see because it's more dynamic event, we have even higher values. You can also see that in this later part, so after 7:15:30 UT, we have the average increase, and this is because this is the time when we shifted to the second ASCAT measurement with higher electron density. So yeah, we have shown that we have two events in which we have extreme heating, which is missed by, well, most of the other instruments. So in conclusion, we have performed a small-scale auroral dynamic studies using our optical instruments. First study was statistical one, in which we got the significant correlation between the flux variability and tangential electric field variability, which we try to explain as both having the same source, which is the variability of non-static, non-uniform current sheet. And also we have the mean flux and flux variability correlation, which we assume is connected with the acceleration process. And finally, this is important because we've done a case study in which we have shown that we have extreme heating during these events. And here I have included a picture from earlier from a LINAR model, just so we can see the values that they're getting from their model, which is the highest value is 18 milliwatts per meter squared, and around Svalbard it's even less. So the whole point is that we are significantly underestimating, and even though these are very short events, if we add multiple of those events along the auroral oval, we might get a better representation of the Joule heating. And that's it. Thank you for listening.